Hi, it's Robin. Back in 2013, this Asteroids game for the Commodore 64 was released by Norbert Kehrer. I remember thinking it was really interesting at the time for two reasons. First, it bills itself as an Asteroid emulator, and that's because it's running the actual 6502 game code from the original arcade game from 1979. Here's Arcade Asteroids running on my Nintendo Switch. So in some sense, this Commodore 64 program isn't a conversion or a recreation of Asteroids, except for code patches to account for the differences between the Commodore 64 and the Asteroids arcade hardware. The code and the game state should be exactly the same as the arcade original. The C64 has to emulate, or I suppose simulate, the vector graphics hardware from the arcade, as the C64 is only capable of raster graphics. There are also the differences in sound hardware and the controls and maybe some other things I haven't thought of. And the second interesting thing about this Asteroids emulator for the Commodore 64 is that a SuperCPU specific version of the game was released. And since I own a SuperCPU, it's always exciting to see a new release for this rare processor accelerator cartridge. And then I learned of another interesting thing about this game. I was contacted by C.O.T.E, who runs a YouTube channel called Commodore 128 Mode 3. C.O.T.E, that stands for Commodore 128, told me that while this game works reliably on the Commodore 64, it's hit and miss on the Commodore 128's C64 mode. It frequently crashes when the gameplay starts. A while ago, I did a whole video about the fairly small number of C64 games I'm aware of that don't work properly on the Commodore 128, so I was very interested to learn that this game was possibly another one for my list. So that makes three things I find interesting about this game, and that means I just had to make a video or two about it. As always, I'll have a chapter index if you want to jump around. First, we'll look at the game running both with and without the help of the SuperCPU at 20 MHz. Then we'll take a look at how the Commodore 64 is able to run the original arcade code, more or less. And finally, we'll start to look at what's up with the game on the Commodore 128. But I think some of that will have to wait for a second video. Now, the SuperCPU specific version, which I've got booted up here, does not seem to crash. And my SuperCPU is plugged in and enabled, but I've got the speed in the normal 1 MHz mode. Okay, so let's try starting the game. All right, so we'll start the game. So at 1 MHz, the game is very faithful to the arcade, but it does run pretty slow. I think it's running around 15 frames a second. I actually did some capture of this at 60 frames a second, the video capture, and I was kind of trying to count frames in my video editing software. It seemed like every fourth frame, the ship and the asteroids moved, roughly. So that'd be about 15 frames a second. Guess it's pretty easy playing in slow motion like this. But you can see, very accurate. Just very slow as well. Okay, but you're not here to see it running at 1 MHz. Let's switch it over to 20. Ooh. There, I did a hyperspace there. If you pull down, you can do hyperspace. Okay, so you can see how much faster everything's running and smoother. So I'm fairly sure it's running at the full 60 frames per second now. Again, I did some capture, and it looked like every frame something was moving. The ship didn't always seem to move every frame, but that might be because just like the game logic. Now, the original arcade had a vector system. And if you're not familiar with that, rather than the raster display, which is drawn essentially pixel by pixel from the top left across the screen, row by row. That's how like a TV works, and the vast majority of video games work that way. But a vector graphic would instead give a list of lines to draw, and either a CPU or some other kind of controller would actually aim the cathode ray to a series of XY coordinates and either turn the beam on or off and draw out a screen as a series of lines or dots, I suppose. Oh, I'm not doing so well while I'm talking here. But that kind of cathode ray tube, in a way, well, you can't really say it has infinite resolution, but it doesn't have pixels per se. At least I don't think it does. Maybe the phosphor on the screen is still kind of like pixels. But anyway, in a way, it was a way of making a sharper image, but it had its own limitations as well. Part of it was refresh rate, that you're just drawing the screen over and over again. And to get that kind of continuous image, you can't draw tons and tons of lines because the earlier lines would be already fading out by the time the new ones appear. Oh, there's one of those little UFOs. Let's get that guy. There. Good. Okay, so what was I saying? Oh, yeah, that... that this is being mapped onto the Commodore 64 screen. I believe it's only 256 pixels wide, not the Commodore 64 screen, but the way that this is being programmed, 256 pixels across and 200 pixels down, and so the vector display is kind of being mapped onto that. So maybe that's why the ship doesn't move every frame, or maybe it's just the logic of it, or maybe it's not a full 60 frames a second. I'm not totally certain. Oops. And maybe it occasionally drops a frame. I'm not sure. It kind of looked like it did for a moment there. Anyway, it's pretty good. It's pretty fast. It's pretty fun, and I think it's the most accurate Asteroids available for the Commodore 64. Especially when you have a Super CPU to speed it up like this. Okay, so if you want to check out more footage of this, please check out, I'm kind of doing a co-op with C.O.T.E. So if you check out his channel, I'll have a link in the video description. And he's taking a look at this game as well, and we'll be showing more footage of it running on the Commodore 128 as well. And he has some ideas about the mystery of why it doesn't work so well on the Commodore 128. And I think he's also looking at some other arcade games there. So anyway, highly recommend you check that out. Either right now or after you're done watching this video. Boom. Oh yeah, C.O.T.E. also pointed out that when your ship is thrusting forward, that you don't actually hear the thrusters. And I didn't look into why that is, if that's just an oversight in the emulation. Most of the sound effects seem to be there. In the arcade, it's a very low rumble. The thrusters aren't particularly loud. That is something to investigate another time. So I'm going to unplug the SuperCPU. And I'm going to plug in my Kung Fu Flash that has the latest Super Snap-P ROM on it. It's an upgraded Super Snapshot ROM from my friend Adrian Gonzalez. Okay, so I was curious how this emulator works. So you can download the game for yourself from Norbert's site. I've got it on my SD card here. And I was running this file, AST, Asteroids SuperCPU. But now I'm going to load up the standard one because I'm running my Super Snapshot and I want to look at the code here. So go into the Super Snapshot Monitor. Check that file name again. Yeah, it's just Asteroid. So I'm going to load it up. Okay, it's going to load from 0801, which is the normal basic loading address. And it loads to 51E6. And so that's the entire game. About 4,900 hex bytes. So what is that? About 16, another 2K, about 18, 19 kilobytes, I think. Now, if we look again at that directory I've got organized here, pay no attention to those fixed files. So my first question was, does this game actually include the arcade ROMs? So I looked online, and because of the prevalence of the emulator MAME and so on, it's quite easy to find these arcade ROMs. So these have apparently been dumped right out of the arcade. I renamed them ROM 1 through 4. Each one of these is a 2 kilobyte binary dump. And I believe the reason they're in 2 kilobyte chunks is that the original Asteroids arcade PCB has 4 2 kilobyte ROM chips on it. I guess they'd be 16 kilobit. Probably in 1979, that was normal size ROM. If you want a huge 8 kilobyte game like this one, you would need 4 ROM chips, 2 kilobytes each. Now, the actual file names I'll put on screen, they're kind of ugly, but I think it's like the 6-digit part number, like 035145, and then a dash, like 0204. Often with chips, it's kind of like a part number, and then a dash, and then perhaps a revision number. And I have heard that there's as many as 4 different Asteroids ROM revisions out there in the wild. And back in those days, it was pretty common to update one ROM, but not necessarily the whole set. It was just like cheaper and easier, I guess, to just patch one particular ROM. So that's why we might have, for example, version 4 of a couple of the files and version 2 for some of the others. I'm just speculating here. Oh, and I'm talking a lot, but basically the game is 6 kilobytes of code. 3 of these ROMs. I think this 4th one is actually graphic data. It might be called the vector ROM, and it actually contains vector instructions for the shape, the ship and the rocks and so on. All right, I'm really rambling here. So what I want to do is load ROM 1, the first 2 kilobytes, into C64 memory and compare it. So what I'm going to do is load it from device 8, that's my SD drive, to C002. And I've explained this before, but basically Commodore 64 load command expects a PRG file. These are raw binary files. A program file is like a raw binary file, except it has a 2-byte header, which indicates the 16-bit load address. So when you tell C64 to load a raw binary file, it's still going to interpret the first 2 bytes as a load address. The way I work around that is to tell it to load 2 bytes later, and then what it'll do is interpret those first 2 bytes as the load address, but then it will ignore it in favor of the specified address. And it's kind of handy because it'll print out what the first 2 bytes were. So if we look at memory at C000, see these are just initialized to 0FF, and then the 3rd byte is in the correct position. So now all we have to do is patch those first 2 bytes by typing in 4C F3, and this is in high byte, low byte format. We just have to swap them just because that's how 16-bit values are in 6502 or 6510 or 8502. It's all compatible. Okay, so now we've fixed those 2 bytes, and there we go. And now if we check memory, we'll see it's there. And if we disassemble at this location I loaded, you'll see that we've corrected the jump instruction, and now, as you might expect, the first 3 bytes of Asteroids are jumping to a specific location. Now, I've loaded up to C000 because it's just out of the way. I believe this ROM actually lives normally at 6800, 6800. But all I'm trying to do right now is get the original ROM, or at least the first 2 kilobytes of it, into memory. And we believe that the Asteroids game, which I've already loaded, the C64 game, which I've already loaded into memory, contains the ROMs in it somewhere. So I'm just trying to prove that. Okay, so if once again, I display the first line here, what we're going to do is a hunt. So if we hunt from 0801, and then 1, 2, 3, 4, 5, 6, just insert that a bit. So what we want to do is hunt from memory from 0801, which is where the C64 Asteroids Emulator loaded, throughout its range to 51E6. And then we want to search for just these 8 bytes, for example. They should be unique enough that we'll only get 1 hit. Okay, so it's hunting through memory for those bytes. And there's a match. So we'll look at memory at 39E5. And if we look at memory at the C1000, the ROM that I loaded in, sure looks similar. Okay, now how can we be sure? Well, if we compare from 39E5 to 41E4, that's 2 kilobytes worth, 800 hex, and we compare it to C1000, we'll be comparing that 2 kilobyte chunk of the C64 program and the 2 kilobytes of the Asteroids arcade ROM. Okay, let's compare. Okay, so it did find, quite a few differences, but that just compared 2,048 numbers. And of course, this is far less than 2,048. So what is this? This is 8 per row times 1, 2, 3, 10, 11, just shy of 12. So 8 times 12, 96 minus 1, 95 differences out of 2,048. That's about 4.6, less than 5% difference. So basically we have a 95% match between the copy of the ROM in the Asteroids emulator and the arcade ROM. So to me, that is pretty much proof that we have the ROM. So I wasn't able to find a real breakdown of what the different Asteroids ROM revisions are. It's possible that Norbert just got an earlier version of the arcade ROMs. Maybe this is version 3 or 2. Like if we look at 3D A1, it's loading A with 1, 2. And if we look at the corresponding spot, I think that's right. And you see how the code's almost identical, but instead, like we're loading 1, 2 here, and we're loading 1. So this might just be a tweak that the original Asteroids programmers made. Maybe it's some patches that Norbert made. I'm saying his name more French now, isn't it? How do you say it in German? Norbert. No, that sounds French still, doesn't it? I can't speak any other language. I can barely speak English. I'm going to start calling him NB. Sorry, NB. Okay, so my goal here isn't to tediously go through all 8 kilobytes of the ROMs and compare them. You're free to do that. All the stuff is available online, and I'll have links in the video description. My main interest was just verifying that there really is ROM code in here with a 95% match. That is good enough for me. Okay, so my next question is figuring out how the Commodore 64 or 128 or SuperCPU, how do they make use of the ROM code? So obviously, it's not going to run just as is on a Commodore 64 without some modifications. Okay, so if we go back to BASIC and we just list, you see there is a sys 2064. Obviously, it's machine code. So let's go back in here. And if we look at 2064, put a plus sign to indicate decimal, and it'll convert to hex. So the program is going to 0810. So here is the code that's executed. This isn't the Asteroids ROM code yet. This is all native Commodore code. Various jump to subroutines. I figured some of these out. This one calls that front menu that you see when you start the game. That shows instructions and the configuration options. But that second one is interesting. If we go to 0865 and we look at this code, what this is a copy routine. It's doing a copy from this indirect pointer at 02 and storing it in the destination at this indirect pointer 4. It's in low byte, high byte format, so it's copying from 39E5. Does that sound familiar? That's where the ROMs were stored in the C64 binary. Copying from 39E5 and copying them up to 6800, which is where the ROMs live in the Asteroids arcade machine in its memory map. So because we don't have ROM there, but we have RAM, so we just copy the ROMs into this correct spot in RAM, and this is a big part of how the ROMs can run on the C64. Just copy them into RAM at the correct location. And so here's a loop, and we're just copying, and basically it's going to copy until it hits a high byte of 80 in the destination. That is in here. When it hits 80, that will be 8,000 hex. It'll have copied from 6,800 up to 8,000. That's 6 kilobytes. And like we had talked about, there's 6 kilobytes of code. So that's being copied into place. Okay, now there's also the graphics ROM, but I haven't looked in detail at that. I want to point out there'll be some links in the video description. There's an excellent website called Computer Archaeology, and there's a full write-up about the Asteroids DVG vector ROM, which is the vector generation hardware. So I'll just show a little bit of that on screen, but I really highly recommend that you check out this excellent website. And there's a full write-up of like every configuration there, rock patterns, the UFO, all the different directions for the player ship. It's interesting that the rotations are pre-rendered into lines. I guess that's just quicker. The live counter, there's a whole font called characters there. All the letters, because Asteroids does show text on screen, it all has to be made out of lines. And messages and so on. Okay, and then back to this main bit of C64 code here. Okay, so title screen, copying the ROMs into place. And here's another big part of the magic. We'll disassemble that 893. If we look here, what's happening is just simply loading an immediate value and then storing it in memory. And you'll notice every one of these addresses is within that range of 6,800 to 7 FFF hex. So what this is a list of patches, poking or patching bytes within the ROM that's stored in RAM. And if you look, all of these, it's just a huge, huge list. Loading a particular byte and then storing it. So I believe this was a huge part of NB's job here, was going through and figuring out where to patch the ROMs. Now you think, look, he's rewritten the entire game. Okay. Well, as long as this list is, okay, it goes all the way to OE2B. So it does go on for like a lot of pages here. Okay, let's do that quicker from there to OE2B. Okay, well, let's quickly scroll through the rest of it. But you see this all follows the same pattern. And there, finally, it's done. I'm basically certain, I'm not sure I read every single line of this, but I believe these were all patches in the ROM. Now, you might say that's a ridiculous number of patches. This isn't an emulator. This is a patch-ulator. I don't know. What? But we can get an idea of how many bytes are patched. As you see, when you load an address, it's this opcode A9 for load immediate, and then the value. And then every store A here, 8D, store A to a 16-bit address, has the opcode 8D. So basically, I counted the number of 8Ds in that memory range, and there are 307 bytes changed with the patching. Now, that sounds like a lot, but again, out of 6 kilobytes, 6,144 bytes. And that, I don't know, coincidentally, is almost exactly 5% again, just like the difference between the two ROMs I had, which again might be just ROM revisions, I'm not sure. So 307 changed bytes out of 6,144. It's almost exactly 5% difference. So that means we have 95% of the Asteroids ROM code the same. So is this a 95% accurate arcade emulator? I don't know. Yeah, just to deal with that, I'm sure some of you don't like that the author called this an emulator. I understand that. So it's running the arcade ROM code on the Commodore 64. So in a sense, it is the Commodore 64 emulating, or if you want to say simulating, the Asteroids arcade game. But that's being achieved by, as we see, manually patching the arcade code with equivalent Commodore 64 code. And there's also some blocks of C64 code that we'll look at in a bit. A lot of these patches are actually just redirecting the arcade code to some new Commodore 64 code that emulates things like the graphics and the sound and the input and the controls. So you might have an idea that a true emulator would just be able to load and run unmodified arcade ROMs on another platform, as most modern emulators do. Okay, so I get that. I'm not going to get too hung up on that. I think it's pretty cool that we have such an accurate version of Asteroids on the C64. And really, it just all comes down to, nerds want to argue about what an emulator actually is. And there's a lot of different definitions if you really look into it. There's a lot of history to it, where the word has changed meanings over the years. It was apparently first used in a computing context way back in 1963 by IBM. And this has become relevant again lately. I've seen a bunch of nerds on Facebook arguing about the new FPGA-based Commodore 64 that's being announced by Perry Fractic and his resurrected Commodore brand. So some say that FPGA is just emulation, and others say, no, it's not. I figure the argument is really about the definition of emulation, rather than, the nerds get caught up on specific examples, and I'm a nerd too. I don't know. I don't care that much. Okay, so we looked at that huge list of patches, but what do they really do? Okay, well, I don't want to look at 307 of them in depth, but I did find a few very important ones, and maybe the very most important one is right near the top. So let's just look at that again. Okay, so this is patching 3 bytes in a row. 20 is the opcode for JSR 0889, and then down here, so this is jumping to location 0889, and then EA is the no operation opcode. EA, so it's just nopping out, meaning no operation in the next 2 bytes, just making whatever was there disabled. So for the next bit, as we look through this, there's an excellent commented disassembly of the Asteroids arcade game available online. And again, I'll have a link to that in the video description. I'll take some screenshots of that source code and show it where it's relevant. Now, this isn't the original arcade source code, but it is a recreation done by some fans who disassembled the ROMs and then have studied it carefully, and they seem to have done an excellent job. So thank you to them for all their efforts. It's been very helpful for me. Now note that the source code for the C64 version is not available, so everything I figured out about it has just been through my own disassembly and studying the existing binaries. So looking at the disassembled source code, we see that there's the main game running loop at 680C. It says load A with the self-test switch, and it branches if it's active. So this is right at the top of the main game loop. Actually, what I should do here is just run the game. Okay, so we started the game. Gonna freeze, super snapshot, go into the monitor. Okay, so we look at the ROM code here, okay, so we saw that the original arcade ROM is actually doing a check for a self-test switch status here, and then branching away if it's true. But instead, these 5 bytes have been patched by that C64 patch code into the ROM to instead redirect to this JSR 0889, and then just to patch out these couple extra bytes here. That would do the actual branch. Okay, so this, I think, is the most important patch of them all, as I was saying. So if we look at that, disassemble 0889, and it's just 3 subroutines, and then it returns and continues. So you got your main arcade game loop. Most all video games ever actually have a main loop that just executes over and over again. And that's how you get that sense of gameplay where the inputs are happening, the logic is done, the screen is redrawn, the sound effects are updated, and that often happens at about 60 frames a second. It can vary, but that's very common. So what's happened is the C64 code has been injected in here, and every time through the game loop, instead just the arcade ROM running, the C64 sort of takes over for a while. Of course, 64 is always in control, but it's that kind of separation. If you think of the arcade game being the ROMs at 6800 to 8000, well, down here at 0889, this is where some of the C64 code lives. And in fact, it's this whole area from about 0800 up into this area around up to even 2000 hex, where these various routines that do the emulation are. And earlier I had taken a guess. Well, it turns out that I was more or less right, that all the tasks that the C64 has to emulate are summed up in these three routines. JSR 121C, this does the graphics processing right here, this routine. And then next, this one here does the control update. It maps the joystick ports to the original arcade buttons. And you might be able to guess that 1802, this handles the audio processing. So the arcade's sound hardware gets mapped to the SID in the Commodore 64 128. And each of these do this by examining the current arcade game state and then doing their best to map that state into C64 equivalents. Okay, so I wanted an example how this might work. And the best simple example I could think of that uses all 3 of these systems is firing a bullet. The player hits fire on the joystick. That's an input. So inputs have to travel from the C64 side and get passed into the emulator, if you think about it, because the joystick is plugged into the 64 and that gets passed in. So inputs have to go from the 64 to the arcade. And outputs, which are the graphics and sound, kind of originate in the arcade or at the arcade side, and then it's up to the C64 to output them to the user. Can I get that? Sorry if this is obvious. I'm kind of slow, so it takes me a while to figure these things out. Okay, so hitting fire is an input. It's on the 64 side, is passed to the arcade. Then the arcade side processes that fire button, and it kind of creates the bullet, creates the sound effect, and then it's up to the 64 side to then output sound and graphics through the SID and the VIC, emulating the arcade hardware. Okay, so let's go through these in the order that the events happen. I don't know if it matters or not. You might think that it would be input here and then output, but the input's kind of buried in the middle. There might be a good reason for that. Maybe there isn't. I don't know. Okay, so that input routine is at 1779. And we're just going to focus. There's so much code here. You say, I don't know how long I've been going already. There's a lot to cover here, so we just have to be very specific. 6 kilobytes sounds like a tiny game, but when you think, man, that's 6,000 bytes. Is Robin going to talk about 6,000 different bytes? No. So anyway, here's the important part right here. The C64 loads from DC01 and DC00 and stores them in these memory locations 17FF and 1800. Those are the two ports on the input-output chip, and these are the two joysticks, essentially, right here. This is joystick port 1, and this is joystick port 2. And it stores them to memory. And then what it does is all these represent the different buttons on the arcade machine. And it's zeroing them all out, and that's going to load the Y register with 80 hex, that is the high bit set. And 6502, it's common to use the high bit as a flag. If you really only care about 1 bit, each of these is really, I think, just a 1-bit value, but you use the highest bit because the 6502 has some easy opcodes to detect that high bit, the minus bit it's often called. Okay, and this one right here happens to be the fire button. So OE33, the fire button zeroed out. And then if we scroll down, B1 and C4, and it seems the way the emulator works is that either joystick can be used. So this bit right here, this is bit 4. They're numbered from 0 through 7. Bit 4 is indicated by this AND. So it's basically checking, is the fire button pressed? If so, then store Y, which is this 80, in 0E33. And likewise, it does the same down here for the other joystick port. And actually, so what some more of the patching does, the actual fire button in the Asteroids arcade game is at 2004 hex, but it's actually being patched to this OE33. Are the patches still in memory? Let's see. Yep, there they are. Okay, so this is exactly where that OE33 is patched into memory. Okay, but we don't have to go through all that. That's what so many of the patches are, though, basically changing memory addresses in the ROM, either for different variables, hardware locations, or patching other subroutines in to handle the C64 side. That's what the vast majority of all those patches are. That's just a very quick look at the input. You get the idea. C64 input registers are checked, and the appropriate controls are put in the appropriate button locations for the arcade code to read and react to. Okay, so now we're going to look at the arcade code for a little bit. So next time the arcade ROM code loop is run, it's going to check if the fire button is pressed. And you can see it's doing that right here. It's checking the fire button location, and it's shifting that high bit out into the carry bit, which is then being rotated into this variable, 63, just a 0-page location. And then the bit command is being used to check that high bit, and branch shift plus, that means that the fire button isn't being pressed, and it just exits this loop. Okay, but if the fire button was pressed, it continues on to this code, and in the disassembly, it's called the find bullet slot routine. So these memory locations here are just a short list of bullet slots, and the asteroid ship can shoot up to 4 bullets at once. You can verify that by playing the game. If you hammer the fire button, it'll shoot 4, and then it'll wait till one of them times out or hits something before you can shoot more. There's actually 6 bullets in total because the UFO can shoot 2, and they're sort of treated as one system, 6 bullets total, but 4 are allocated for the asteroid ship and 2 for the UFO. If it finds an empty slot, it branches ahead and it puts the number 12 hex, that's 18 decimal, in that slot. And this is actually a time to live. So normally there's a 0 in there indicating that there's no bullet active in that bullet slot. Once a number goes in there, above 0, then that's the number of frames that bullet's going to live. So they last for 18 game frames, nearly a third of a second. Okay, and then there's all kinds of other code that we're just looking at this tiny bit with about how the bullets are managed. But you can imagine that All the different objects all have their own ways of being managed. They have X and Y positions. They all have, whether they're alive or gone, or the player's ship can be in hyperspace. It can be exploding. It has all these different states, and the game tracks all that. And likewise, bullets are tracked for position, for velocity, X and Y, their time to live, and so on. So there is a whole bunch of other logic here that the bullet copies the player's position and then figures out the velocity based on the angle of the ship. There's quite a bit of math and logic that goes into all this, but we will not get into all that in the interest of time. So that's all this code here, figuring out the bullet. And the final thing that's done, though, as part of shooting the bullet's being spawned, it's all set up, and finally this right here, load A with 80, and stored in this location. This is a short list of sound effects, and this triggers that sound effect. So you can see that the game code doesn't try to start the actual sound effect yet. It just basically flags that sound effect, the shooting sound effect, needs to be played now. And of course, it's going to be up to the C64 to actually handle that. Okay, and also in the source code, I'll just show a quick screenshot of it. There's the main, well, I call it source code, but the disassembly of the Asteroids arcade. There is also an Asteroids define file, and it has things like the ship X position, the bullet X position, and so on. So just so you know that there is this other file that has all these labels defined along with their memory location. And that's actually a very useful file. If you're trying to understand how this whole game works, that's a very valuable file. Okay, so the arcade still has to do a bit more here. Okay, so it's been going through checking different slots, so to speak, but now it's time for it to check whether the ship fire sound effect should be played. So that's selected it with this X, decrement X. And then it goes to this routine called Start Sound Effects Timer, if applicable. And then if so, it'll return a value that then gets stored in this OE50. This is another patch value. It was something else in the arcade, but for the C64, it's being patched to this value. And that is the sound effect status for the shoot sound effect in there. Actually, we can look at that. Start SFX timer routine. But this is where it finds that the bullet fire sound effect should be triggered. It checks it right here. And if that's set, then it's going to branch to that 75DD right here. And that's actually a list of all the timers. And then it branches, or it gets over to here and executes. And it stores here the sound effect status. Sorry if I mentioned before. Oh yeah, this is the status here. This is where it's checking if it's available. And this is where it is actually setting it. Yeah, that's like a branch always, isn't it? And that's where it's setting the sound effect status right there. Okay, back to this little list of these are the graphics, input, and sound. Okay, so that 1802 is what handles the audio. Okay, it does a whole bunch of stuff, but we're looking specifically for that sound effect. You can see here that it's writing, these are the SID registers right here, D407 and so on. We're looking for 18E7 right here. This is the ship firing a bullet sound effect location. So we're going to check if it's being triggered, and we compare it against 19A2, which is a stored copy of that register. And if it's equal, we're just going to be done. We're just branching ahead and out. There's nothing to do because there's no change in sound effect state. But if it is different, then it's going to load the new status or the new value and save a copy of it. And this is like a branch always, this to 1906. So this means we're starting a new sound effects. Let's go ahead to 1906. That was a good year. And this is where we're triggering the sound effect. And it's saying the frequency of voice 2 to 3000, and it's enabling the sawtooth voice and then gating the sound effect. That 1 bit starts a sound effect on the SID. Okay, so it's a simple sound effect. Pew, 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 pew. The original pew, pew, pew. Okay, so there's more to it again, but again, you get the general idea. Arcade side requests the sound effect, and then the C64 side sees it and tracks it and triggers the actual SID sound effect. Okay, so next, finally, we're going to deal with the graphics. And this is the most complicated section. Jumps here to 12.1c. Okay, so how is the bullet rendered? It's actually pretty complicated, so again, I will not go into every last detail. First, we'll look at how the C64 hardware emulates the vector display of the arcade. So the vector graphics are simulated with the Commodore 64 bitmap modes. It's 2 8KB bitmaps, double buffered. One is displayed on screen, and that's the one, there's one at 4000, and there's also one at E1000 hex. And basically it just shows one while it's drawing to the other, and then once that one's ready, it shows that one and draws to the other one and just swaps. And it's just a way of smoothing out the graphics and reducing the amount of flicker and redraw that's visible. It's a technique that's used all the time. Modern systems use as well, because it's probably like triple or quadruple buffered or whatever. Okay, and the arcade hardware, I haven't mentioned this yet, just as yet another sidetrack. It has this vector RAM, which is basically a display list for the arcade machine's DVG, the digital vector generator. It's a display system. It's actually like a coprocessor, and it runs independently of the 6502. So you got 6502 in the arcade running at 1.5 megahertz, and then it's also got this DVG in Atari fashion, kind of a coprocessor. It has a small set of instructions, and basically it processes a list of graphic instructions. And it can either do that from RAM, or it can actually do it from ROM. So part of the list might involve jumping into that vector ROM we were talking about earlier, where it's not just the raw ROM data, but it's actually the instructions to draw those shapes and so on. So they don't have to bother drawing them into the RAM as well. It can just be in ROM. Okay, but we're just going to look at a very simple part of that. We're just looking at the bullets, which aren't complicated shapes. They're just points. Sorry if you're not satisfied with that. This turned out to be such an enormous task. I've been working on this for weeks, just trying to put this together. We'll just get right back into the bullet firing example. Again, check all those other links in the video description to learn more about the DVG and so on. Okay, so this whole 1200 area, it actually gets all the way to 14.9D. So we're already, 700 bytes or something into the C64 graphic routines here. And we get to this bit here. And we're going to load Y with 0 and X with 5. And that's the number of bullets to process. I mentioned that there's 6 in total, 2 for the UFO, 4 for the player's ship. And basically we go through this list, and this looks for any active bullets. And it's at 021D. Okay, so basically this is looked up, and I think we mentioned that this is like a time to live. So basically if you shot a couple bullets, then one might have 8 frames to live, and one might have C, and so on. So if they're still active, they keep getting decremented every time through. It's both, yes, this bullet is active, and this is also the time to live. When the time to live goes to 0, then the bullet's not active anymore. Kind of 2 birds with 1 stone there. If that slot is equal to 0, it just goes and processes the next one. Well, it doesn't branch up. It actually branches the bottom of the list, which then decrements X and goes back to the top. But if it is active, then it stores the current bullet index in this memory location, and then it starts looking up the X and the Y position of the bullet. And there's a corresponding table for each of those bullets with their X and Y position. Here's where the low byte of the y coordinate is loaded. And here's the high byte. The two are together shifted 3 times, which is equivalent to multiplying by 8. Okay, so what it seems like is that essentially they've got a 13-bit resolution for the x and the y coordinates. So it's 13 bits. We shift it 3 more bits to the left, multiply it by 8, and you end up basically with a 16-bit value. And then we just take the high byte of that at the end, and then that has changed a 13-bit value, scaled it down into an 8-bit value, which is 256 X positions, which I had talked about earlier. That's how, the C64 bitmap is actually 320 wide, but I don't know, for ease of programming or just to keep the aspect ratio right, it's 256 across that's actually being used. So when we take a 13-bit value, multiply it by 8, it's the equivalent of changing it to 16-bit value. Of course, the low 3 bits are just 0. But then we truncate that, we end up with 8 bits. So it's a way of like scaling the value quickly, or relatively quickly, as quick as the 6502 can do it. So that's really what's happening, is we're just converting the 13-bit values that the game uses internally into 8-bit values that the C64 can display on its bitmap. Okay, and then the same sort of thing is done here. We can find a multiply by 8 here. That was the y up here, actually. I said x, but this is the y, and down here is the x. Oh yeah, and the y is also checked. The C7 hex is actually 199 decimal, so it's actually checking for y clipping because the screen is only 200 pixels tall on the Commodore 64, and I think it just throws out anything that doesn't fit in that range. So really all this code is scaling the vector coordinates down to C64 pixel coordinates. So the x is now moved to x. Oh, and back up here, the y value was put in the y register. So basically all that to get the pixel coordinates into the x and y registers. And then it calls this 22FB, and that is a pixel plot routine. 22FB. Which again actually checks for a y. I'm not sure why it does that twice. Y. Checks for the 199 again. Maybe some other uses of this routine don't do that check ahead. I do see some inefficiencies in this code, but I'm not complaining. It's like a pretty amazing feat. I don't know if I could have pulled this off nearly at all. So I'm not going to criticize it, but just some of you are probably watching saying that could be made better, Well, yeah, it probably could, but still pretty good. Once it's being boundary checked, then there's these tables here that are 256 bytes each. They're just a quick lookup table to translate to bitmap coordinates because of the C64's kind of funny layout with, it does 8 bytes in a row stacked, then it goes to the next one. It just echoes how the character mode works. And just making it table-driven is by far the fastest way to do a pixel plot. And right here is just a little check for which bitmap mode are we using. Is it plotting to the 4001 or the E1001? If it's the 4001, then it's done. But if it's the E1000 bitmap, it has to add A0. 40 plus A0 is E0. So this is just code to choose which of the two bitmaps, the double buffered bitmaps, it plots to. Okay, and this is, again, this seems a little bit long-winded, but anyway, it's the pixel plot routine. It's obviously not terrible. Well, and there's a little table here. The x-coordinate gets turned just a modulus of 8. You end up with an x-pixel from 0 to 7, 0 to 7 for each spot. And there's a little table here at 2, 3, 4, 7 that just flips the bits quickly here. When you have to turn on a particular bit, it's actually opposite, where the biggest number is at the left and it counts down bit by bit down to 1 at the rightmost pixel. So you just have to keep that in mind. So it does the conversion and it ORs it with what bits are already there so it doesn't accidentally erase other pixels and stores it back in. And then it is done. I know I hurried through some of that. I'm sorry. We could look at this for hours and hours and hours. 6 kilobytes of ROM code is like 3,000 lines of actual code, plus like if you have labels and nice formatting, it's even longer. So it's still a lot to look at. And then there's all the C64 code as well. But I hope that's like an overview just to see, we're looking at kind of how the arcade works, a little bit of it, and how the C64 side works. Okay, so now we're just going to move on quickly to the final aspect I want to cover today. C.O.T.E said that this game crashes on his Commodore 128, and in fact, it's crashed lots on me today. When you try to start the game, when you go from the menu to the beginning, it's very crashy on a Commodore 128. If the game starts, then it's good. Like when you get to the title screen, you press the button and the Asteroids game appears, you're fine. But it crashes often there. So I was curious, is it a weird compatibility problem with the Commodore 128? Well, not really. As part of that initialization, we'll just skip ahead here at 2712. Okay, it does some copying. Yeah, there's actually this overlay mode that kind of simulates the colored overlay that some Asteroid arcade games have. That's where that's all done. But if we keep scrolling down to 27CB, so there's all kinds of initialization code. This is just the C64 mode gain setup. CB, here we go. Okay, and this is how we know it's not really a weird compatibility problem with the Commodore 128. This is actually Commodore 128 specific code. Load A with D030. I covered this in that Commodore 128 episode. This is a special bit in the VIC-2 that's only on the Commodore 128's VIC-2. And this is the speed up register. You can read this. If it returns an FF, then you are dealing with a regular Commodore 64, and that's the end of it. If it is a Commodore 128, then it's running code specifically for the Commodore 128. So I don't know if this only got tested on maybe a PAL Commodore 128 or just on emulator or whatever, but I know on NTSC Commodore 128s, this code is extremely crashy. This is definite proof that the intention was do something special if running on a Commodore 128. And this is only in the C64 version. It's not mentioned actually in the documentation, interestingly. So I don't know if that's because it didn't work very well or forgotten. Okay. So basically this routine is only called on a Commodore 128. And if we look at this code, it actually turns off regular interrupts and enables a raster interrupt. Actually, that was done earlier, just to see that part. This is how the raster interrupt is configured to 2858. So basically, if it's a Commodore 128, then it sets up to run this code on a raster interrupt. And it's this code right here, 2858. And right here is what we're looking for. This is code that, based on the raster line, will enable and disable 2 megahertz mode. That's what this D030 register is. If it's set to 1, it's in 2 megahertz mode, but that actually causes the VIC chip to not be able to display graphics anymore because the VIC can only run at the regular 1 megahertz speed. So it's a common, you probably already know, it's a common Commodore 128 trick to enable 2 megahertz mode, but only in the top and bottom borders during vertical blank, roughly, switch to 2 megahertz mode, and it boosts the speed of a Commodore 128. Well, it's 2 megahertz for that section of the screen, and the net result is being 20-30% faster than a Commodore 64. And you can imagine this was done because this Asteroids emulator is a bit on the slow side and can use all the CPU help it can get. And while most people do not have a super CPU, a lot more people do have a Commodore 128, and this is a nice little speed up that's available. So that's obviously the intention here was speed up the Commodore 128 if it's available. And actually, the game does run better. Let's see if it'll actually resume here. I think you can see that the game is running noticeably smoother than the 1 megahertz that I was showing you earlier. I mean, it's still bogging down a bit. It's not as good as with the Super CPU. But I think it's pretty obvious it is a lot better than the 1 megahertz C64 mode. Quite a bit smoother. I can play 1 megahertz mode next to it in case you don't believe me. I'm not playing very well here. Okay, so 30% for free is pretty good. And actually, maybe this is even better than the 1 megahertz SuperCPU code that we were doing earlier. This is more than 30% better. I didn't actually study all that. There's been so much to this already. So what we have here doesn't seem to be the Commodore 128 being incompatible with Commodore 64 code, like some of those other games I looked at in that Commodore 128 video where there were actual bugs that would work properly on a Commodore 64, but crashed on a Commodore 128. In this case, it's like we have Commodore 128 specific code that would never be run on a C64, but there's something crashy about it. There's a bug in there, and I think we need another full video to really find the cause of that crash. I think we've got a rough idea, and we'll also try to fix it. And there's actually, I think, at least 2 bugs in here. So I do have it mostly figured out already, but to get all my notes in order to make a video about it, explaining it, I'm going to need more time. Okay, so thanks very much to NB for his work on this. You know, too bad about the crash, but all the rest of his excellent work. It's kept me very amused for a couple weeks now, studying this and enjoying even just playing the game, especially with the Super CPU. So it's a great job, and who knows, maybe we'll get a newer, updated version of this after this video comes out, where NB will fix it up a bit. Also, thanks to C.O.T.E over at Commodore 128 Mode 3 for bringing this to my attention. Please go check out his channel if you're into the Commodore 128, and check out his video where he'll have more of a look at this Asteroids game. Okay, and hopefully I'll be back soon. We'll really dig into what's going on here. I really have found it very interesting. Okay, thanks to my patrons for their support. Thank you for watching, and we'll talk to you next time.